Okay, so dilations. Now, what are dilations? Dilations are the way we want to think about this. We want to relate this to stuff we've already talked about. So remember, last chapter we talked about isometries or isometric transformations. And we said that those things were, remember, those are all the ways that we can take a figure in the xy plane. Alger, get up here. Those are all the ways we can take something in the xy plane and we can move it around without changing its size or shape. So that if we start with the blue pre-image and we do one of those transformations on it, and we'll come up with, we always made it a red image. The image and the pre-image were congruent, right? What were the three ways that we could move things around on the plane and not change any of the measurements?
Rotation.
Okay, rotation was one. What's another one?
Translation.
Translation. What's another one?
Reflection.
Reflection, yeah. Okay, so those are the three. Now we're going to look at one today at a transformation that is not isometric. This one, it does not preserve all the measurements. They're going to change. This time, the image and the pre-image, instead of being congruent, are just going to be similar, but not congruent. Okay, and what this is called is a dilation. Okay, now there's a great way to think about dilations that will make this really, it'll give you a great mental picture that describes this. Here's how you think about it. A dilation is like if you take a camera lens, a zoom lens, and you're going to point that zoom lens at something. And that something, the very center of the lens is what we're going to call the center of the dilation. Okay? And then if I zoom in or zoom out, I want you just to think about what happens to the things in the lens as you're looking through the camera. For example, let's say that we're focusing on this XY plane and we're going to point the lens right at the origin. Okay? And I want you to tell me what's going to happen to that blue triangle as I zoom in. It's going to get bigger. Okay, for one thing it's going to happen is it's going to get bigger. Absolutely. Okay, what about its location in the lens? What is it going to stay in the same spot? Ah, okay. Yeah, if I'm pointing the center of the lens right there, wouldn't you agree that as I zoom in, this blue shape, this blue triangle is going to move up this way and get bigger? Can everybody kind of visualize that? Okay, if I zoom out, opposite will happen, right? It's going to get smaller. It'll move in towards the center of the lens. Does that make sense? That's a dilation. That's exactly what a dilation is. Dilation is just our mathematical way of describing that. Okay, so let's do a dilation and let's see what happens here. Now, one thing I'll tell you right now is that when we do dilations, and that's a word, to dilate is a word that you might have heard. I mean, like your pupils dilate, right? They get bigger, right? If your pupils dilate, that means like when you're in a dark room, the pupil on your eye will get a little bigger to let more light in, right? But when it's real bright outside, it will constrict and it'll get smaller so it doesn't let as much light in, right? Controls the amount of light entering your eye. So it makes sense that this is a word that we would use for something like this. Now, a dilation has a scale factor associated with it, just like all the scale factors we've been talking about when we've been working with similar triangles. That makes sense if you think about it, because I just told you that a dilation, when I dilate a pre-image to create an image, I'm going to get a similar figure, right? So the scale factor obviously has to be there, has to relate those similar figures. The scale factor has more meaning with the dilation than it normally does, though. It's even more important. The scale factor for dilations, we always let equal small k. That's sort of the symbol or the letter that we use to represent that for some reason. Okay, now let's do this here. Let's look at what happens if we dilate this thing. So I'm going to take all three vertices and all three sides, and let's do a transform menu, and I'm going to go down to dilate. Okay, now in addition to translate, rotate, and reflect, I now get dilate. So there's the center of the dilation, right where I said it was going to be. And it says dilate by some fixed ratio. Okay, so I'm choosing the scale factor here, essentially. So the bottom is 2. I'm going to make the top, how about 4? Okay, so if the top is 4 and the bottom is 2, that's the scale factor. What does that reduce to? 4 over 2. 2, okay? 4 over 2 reduces to 2. So my scale factor is 2. Now watch what happens when I do the dilation. Okay. Now I want you to try to tell me. Let me make that red. Because we always had our images were red, right? So there's the image. And if I go up, I won't do all these, but like this was point P, R, and S. If I ask Geometer Sketchpad to label that point, what's he going to call it? Yeah, it's going to be P prime, then I'd also get R prime and S prime. But I'll just do the P for now. That's all we need. So show the label. There it is. There's my P prime. Now, what about the red image would indicate that it has a scale factor of 2 relative to the blue pre-image? Somebody tell me one thing. What do you think?
The lines change.
Okay, the lines change in what way?
They get longer.
They get longer by a factor. And how much longer? 2 times as long, right? Because the scale factor is 2, right? If I were to make that scale factor 3 instead of 2, where would the red triangle have been? Up further, and it would have been bigger. Everything would have been 3 times as big. Okay, what else about that scale factor, about those 2 triangles, is related by that scale factor 2? Yeah, anybody else want to guess something? And this ought to kind of make sense based on what we've talked about over the last chapter. What else? What do you think?
They're similar. They have all the same angles.
Okay, they have congruent angles. That's true. All the angles are going to be congruent. Very good. What else? What else about it, though, that scale factor of 2? We said the scale factor is K, and in this case, K equal 2, or 2 over 1. What else about that? The side lengths all increased by a factor of 2. Anything else that's related to that 2? What do you think?
The distance away from the edge.
Very good. The distance away from the center of the dilation. Okay, so the distance from P to the origin, right, to the center, that should be, when I dilate this, the distance from P prime to the center should be twice as far away. Okay, does that make sense?
Yep.
And I could, last period I measured these up here, but just believe me. I mean, I could make Geometer Sketchpad measure all that stuff, but can you see that that's the way it's going to be?
Yeah.
Okay, so the scale factor, and that shouldn't be surprising, should it? Because think what we said about scale factors. The scale factor is defined as the ratio of corresponding parts of the figures, right? So if I took the length of R prime, or P prime R prime, and compared that to the length of PR, it's going to be twice as big because the scale factor is 2, and those are corresponding parts, right? Everybody agree? Okay, but the other thing we also said is that the scale factor applies to any corresponding linear measurements. They don't even have to be parts of the triangles in this case. Like, for example, we looked at perimeter, right? We said that because perimeter is a linear measurement, I'm measuring it with a ruler or a tape measure, the perimeter of the red triangle would also be twice as big as the perimeter of the blue triangle, right? The other thing that we could do is we could make a measurement from the center of the dilation. So that's really not surprising because that's also a linear measurement, isn't it? We would measure this distance in centimeters or meters or inches or something if we're measuring the distance from P to the center or P prime to the center, right? Okay, so now what do you think, what am I going to do? Here's the next question. So there's a dilation. What do you think I'm going to do if I want to, instead of, well, here, tell you what, let me show you one other thing. Let's just, okay, what if I dilate this by, if I dilate it by 6 over 2 or 3, I mean, that's expected, isn't it? Right? It's just going to get further away and bigger, right? Okay, but what if I want to, instead of doing enlargements like this, those are both examples of enlargements, what if I want to do a reduction? What if instead of zooming in on the lens, what if I want to zoom out and make things smaller? What do you think? By a negative? Let's try that. See what happens if I dilate by a negative. Okay, let's see what happens if I do that. So I'll dilate by, say, -2. So instead of a +4, I'm going to make it a -4. Well, look what it did. That didn't make it smaller. Ah, okay. Now, first of all, this is interesting what this did. Notice that what this did, instead of making the distance twice as far away, it made the distance from the center to P. Now that's P prime, right? It made it twice as far away, but in the opposite direction, right? Instead of moving away from the center, it actually, we went through the center a distance of twice as far away. Does that make sense? So the negative effectively rotated this thing 180 degrees and made it bigger. The negative did weird stuff, right? That's not what we were looking for. But the suggestion is a decimal. What kind of decimal? Like 1.3?
Sure.
Okay, let's try 1.3. Oh, okay, hold it. Now which one? 0.3 or 1.3? Oh, let's try 0.3. Okay. So transform, dilate, and if I'm going to do 0.3, that would be the same as 0.6 over 2. Okay, so let's try that. This would be 0.3. Ah, that worked, didn't it? Everybody see that? Does that make sense? Why does that work? Well, if K is the scale factor, and here's the way we define K, right? K is the scale factor. And what that really is, that's going to be, think of it this way. The scale factor is going to be the measurement on the image. And I should make that red. Let's see. Yeah, I want to make that red. Okay, does that make sense? The scale factor is always going to be defined as an image measurement divided by the corresponding pre-image measurement, right? We start with the blue pre-image and end with the red image. So if I were to measure, for example, that distance divided by, from there to there, divided by the distance from there to there, I'm going to get a fraction that's less than 1 now, right? Like 0.3 in this case, 3/10 mean, right? Does that make sense?
Yep.
That also means that the distance from the origin to P compared to the distance from the origin to P prime, it's only going to be 3/10 as far, right? Make sense? Okay, good. All right, the last issue then. All the examples we've looked at here have involved, they've involved dilations where all the vertices, let's get all the phones away, please. Phones away. They've all involved dilations where all the vertices were not on the center. They've all been, none of it's been actually on the center of the camera lens. Okay, but what happens, you suppose, if one of these vertices was actually on, on the camera lens? Like for example, let's say,
You make the shooter bigger or divided, like when you have a picture in Word, you expand it.
like what if I do that? What if I put S, point S, right on the center of the dilation?
The shade is just going to go over the top of it.
Okay. That's the. Okay, what do you think is going to happen if let's say we're going to enlarge this and make the scale factor 1.5. What do you think, Garrison? Okay, so point P prime is going to end up where? Up here a little bit. R prime ends up there a little bit. Where does S prime end up? Same spot. Okay, let's see if that works. Let's try it. So 1.5, I'll make that 3. And how about that? Yeah. That makes sense? Okay.
How come the other image didn't
The other one, well,
on the lens?
because you mean the vertex that was on the, here, you mean why didn't that one move?
Yeah.
Because it was right on the center. And think about what happens with the camera. If I focus in or out, the one thing that's in the exact center of the lens stays put. Everything else is going to migrate. Right? Does that make sense? Okay. Okay, so then real quick, I'm not going to belabor this here. I just want you to make sure we get all this straight. There's very little that you need to see on this. But if we had to look at one thing, we said K was the scale factor, right? I could measure that as the ratio of the corresponding parts of the image to the pre-image. The other way we can do it that's almost easier is to just look at the distance from the center to P prime compared to the center to P. For example, like look at this one. Is that, if we're starting blue and ending red, is that enlargement or reduction?
Reduction.
Reduction, right? So then C to P prime, right? To the image, not the pre-image, but where I finally end up, the distance from the center to where P ends up at P prime is 3, right? C to where P starts is 6. And so the ratio would have to be 3/6. How do you remember easily if it should be 3/6 or 6/3? Well, you told me it's a reduction, right? If it's a reduction, the fraction has to be less than 1. And so the smaller part has to be in the numerator, right? Make sense? So that's a reduction, scale factor 1/2. What about this one? Starting blue, ending red. Would you agree that's a, say it again? No. Enlargement. Okay, that's an enlargement. And for some reason it doesn't have, the 5 on there, but there it is. So the distance, the final distance is 5, the initial distance is 2. So the scale factor's got to be 5/2 or 2.5. Right? Make sense? I think we're good. Okay. 209.
Have a long night.